Welcome to A-Level Physics, Cambridge A-Level. Today's topic is topic 4, forces. In dynamic, topic 3, we look at force causing motion and calculating the resultant force. That means force causes acceleration. The resultant force causes acceleration. In forces, we look at Newton's first law of motion to look at forces in equilibrium. Right? Not resultant force. Newton's first law. Right? This is Newton's first law of motion. An object at rest will remain at rest, and an object in motion continues in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Right? Unbalanced force is a resultant force. Right? So this topic we are interested in resultant force is zero. No resultant force. So the object is either stationary or if it's moving, it will continue to move with constant velocity. Yeah, it can move. Object can be stationary or moving with constant velocity. Right? Resources will be posted here. Physics AS. Others that you may want to visit will be past year paper. I think most of it in PowerPoint solution for before 2020. Same with the practical paper 3 is paper 1 and 2 is paper 3. Okay, let's just summarize what you're going to study. It's called forces, density, and pressure. Right? They will be interested in upthrust, upward force by the liquid on the object, a ball, example. Tension in the string and weight of the object. 4.1 is turning effect of forces. That's what we are interested in. Moment, force by perpendicular distance. Or if you are given A, not D, this is a perpendicular distance. Right? So it's FA sine alpha. Right? It's moment of a force. We use this one. This is a pivot. When we apply force, this is a couple. And the couple cause a turning effect. Two forces form a couple. And the turning effect we call a torque. And we study principle of moment under equilibrium of forces. So this video will cover basically 4.1, a bit of 4.2. Right? This part we will be covering. And you'll be solving things like this one after we cover this topic. Density and pressure, a separate video. Okay, so this one summarizes to you what we will study for the whole of this topic, forces. Some of the older books that you may want to use. Okay, type of forces. We are looking at syllabus 4.2 under number 3. Use vector triangle to represent coplanar forces in equilibrium. Type of forces. Some type of forces, gravitational force and weight, which we have introduced in topic 3. Electric force, we will not be interested in that yet. That will be in topic 18. Thrust, that's the force provided by the engine of the vehicle. Friction or drag, right? That's a resistive force to motion. Upthrust, or some textbook will call it buoyant force, American textbook. Magnetic force, you will study in the A2, topic 20. Okay, equilibrium of a particle or equilibrium at a point. That's what we are looking at. So Newton's first law of motion, the body should be the center of gravity of the body, where all the forces pass through the center of gravity, or it could be a particle or a point. Newton's first law of motion tells us that for a body to be in equilibrium, the resultant force is zero, or forces are balanced. It may have forces, but the forces all balance out, no resultant force. Body is either stationary or if it's moving, then it's moving at constant velocity. Example that we have encountered previously in topic 3, under non-uniform motion, where we drop a ball, the velocity will start to increase, that drag will start to increase until the drag is equal to the weight, then the body moves the maximum velocity, which we call terminal velocity. That's equilibrium, right? Where W equals to D. Two person pulling, no resultant force. Forces acting at point P, that's your point P. F1 is balanced by force F2. F1 is pulled by this person, F2 is pulled by that person. So they are equal, F1 equals F2, no motion, stationary, or they stay at rest. Force to the right equals to force to the left. Right? The force balance. Review of vectors. When we study vectors, force F and S, we replace the two vectors with a resultant force R. Right? We have our F. We can use a parallelogram rule. We complete a parallelogram, or in this case, is rectangle, and find the resultant, which is the diagonal, all start from the same point. This topic, we are not interested with resultant force, but what we call equilibrium, which is the same magnitude as the resultant, but opposite direction. Right? So we can replace the R with equilibrium. R will cause acceleration if there's a particle here. If the force E acts, the particle will stay stationary. R and E are equal, but they are opposite in direction. And the force form a closed triangle. We can show that. There's your F. There's your S. There's your force. S is a force. And there's your E. If the resultant force, then it's in this direction, pointing outwards there. You can also use component instead of two forces there. We can use component methods to find the resultant or equilibrium. We replace each vector. These are the two vectors with perpendicular component. In this case, we can draw a rectangle, and then we have our component in the y direction, component in x direction, and then replace that one, and replace this one, same, from using a triangle or triangle, right? Replace it with the horizontal component in x direction, component in y direction, then we just remove it. Then we can find the resultant force in x and y direction. This is 3 square, this is 2 square, so we still got 1 square. Right? This is 5, this is 2, so this is 7. 2, 4, 6, 7. To complete a rectangle, right, in the y direction, the x direction, complete the rectangle, and then find the resultant. A mass held by two wires. We should know how to draw the forces at the point P. T1 is the tension in wire 1. T2 is the tension in wire 2. W is the weight, act vertically downwards. So all the three forces pass through this point there. Three coplanar forces in equilibrium. Their line of action must pass through a point. We call that concurrent. All the three forces on the same surface, on the same plane, must pass through a point. In this case, the point is P. Right? Coplanar means on the same plane. And you can draw the vector triangle. Right? You can start with any vectors if you want to. I start with W because the W is easily defined. They must form a closed triangle. Right? Here's W, here's your T1, here's your T2, and T1. This vector triangle, this vector equation tells us how do we add all the vectors. Right? We start with W, and at the head we add T2, at the head we add T1. So it forms a closed triangle. Or in this case, it's all anti-clockwise, pointing in anti-clockwise direction. Or sometimes it's better to draw on the diagram itself, especially if you are required to show which is larger, which is smaller. Right? So T1 parallel T1, and that is your W as a vector triangle. Three forces in equilibrium, the line of action of the forces must pass through a common point. Right? We say the forces are concurrent. Right? There's a trapdoor. It can be at the ceiling, or it can be somewhere far away from your house. Right? A drawbridge is also a trapdoor. Drawbridge acts as a door, prevent intruder from entering the castle. And there's a trapdoor. Show the forces acting on the trapdoor, the weight of the trapdoor, tension of the cable, reaction force at the pivot from the wall. Give the order and magnitude of the forces from the smallest to the largest value. Right? There's the cable, there's a trapdoor, there's a pivot, there's a wall. So center of gravity, point C, as your weight, where the weight will act from the center of gravity. Right? The cable is pulling on the trapdoor. You're looking at the forces acting on the trapdoor. That's the cable. Tension. So how do we draw the third force? Right? Remember, the three forces must pass through a point. The line of action pass through a point. So that's the line of action of the weight. There's a cable. So the line of action of the reaction force will be from pivot to here. So that is the direction of your reaction force, R. And you can write our vector triangle, W, T plus T plus R. Right? It's not an algebraic equation, it's a vector triangle. That means you must draw the diagram showing the direction of the vectors. Right? Vector triangle, start with W, vertical downwards. Then we can draw our T, parallel. And finally our R. Right? According to our diagram here, R is the largest, T is the smallest. Okay, so it depends on your drawing. Right? It must be quite accurately drawn, roughly quite accurately drawn. Or we can draw on the diagram itself. That's the weight. Right? There's tension a cable. That's the reaction. Okay. So in this case, it's not very clear whether R is larger or W is larger. Right? A bit of ambiguity. Looks like W is the largest. So it's very important you draw on the diagram. Maybe we can do experiment in the lab. Show forces in equilibrium must pass through a point. Okay. There is the weight. The weight provides the tension in the string. There's the weight provide the tension in the string. Right? The pulley just allow you to change the direction of the force. And we can move the pulley to change this angle. We can measure the angle using a protractor. Or we can hang the pulley outwards there. And we can have three strings. Join it to three different weights. The weight provide the tension in the string. Okay, that's a force table. Right? These are different ways of doing the experiment. Show the show that forces are in equilibrium. Or this is a partial question that came out in exam years ago. Right? There's a Newton meter. Allows the magnitude of this force to be measured at an angle theta. You use a protractor to measure that. Consider the force acting at point B. That is a point B. mg is the weight pulling downwards. Right? Weight of hanger and sorter mass. F is the tension measured using the Newton meter or spring balance. P is pulling horizontally on B. Okay? We are not interested in B. We're interested in measuring F, measuring this angle. In this experiment, you will vary theta and angle and read that force. Right? So we can draw. There's a force. There's a weight, mg, and there's a p. This angle there. This angle is 180 minus. This angle is theta. So this angle is 180 minus theta. Okay, redraw that on this diagram. Again, this is a vector equation. Okay, so we look at this triangle. mg sine 180 minus theta is mg over f. Right? As sine 180 minus theta is equal to sine theta, can rewrite the equation mg equals to 1 over sine theta. This for your info, extra info, how the examiner derived the equation. And you're supposed to measure this angle, measure this force, and plot a graph of f against 1 over sine theta against f. Plot a graph of f against 1 over sine theta, and you should get a straight line passing through the origin. Okay, turning effect of forces. So far, we have encountered resultant force causes acceleration. And there's a resultant force, the body or object accelerate. A force can also cause turning effect, rotation. Right? So that's your syllabus. Understand that weight of a body may be taken as acting at a single point known as the center of gravity. Define and apply the moment of a force. Understand that a couple is a pair of forces that acts to produce rotation only. Define and apply the thought of a couple. Right? First thing, center of gravity. Memorize of a body is a point where the weight of a body is considered to act. Right? Yes, some people call it C. That's your point. Center of gravity of this plate, right, or rectangle, or circle is the center. You can call it G, you can call it C. For meter rule, is the center of the ruler. For uniform sphere, is the center of the sphere. For rectangular plate, is the point of intersection of diagonal. These are diagonal. Where they intersect, there's your center of gravity. Center of mass of an object, this for info, is the point at which an applied force produces acceleration but no rotation. It's the same point as center of gravity in a uniform gravitational field. Right? You can see that the center of gravity can change depend on this person is stretching, this person is bending, right? It changes. So this given you the center of gravity of different object there. Stretching or bending changes the position of center of gravity of a body. This experiment that has came out in the practical paper 3, where the students are required to find the center of gravity, and they are required to cut a cut, in this case a cut at different angle, and then find the center of gravity. This one is compound pendulum, 2005 June, paper 5. Right? Of interest is point P, which is called the pivot. There's a point P, the pin there. The hole that the pin make is a pivot. So there's a pin called a pivot. There's a meter rule. There's a center of the meter rule, center of gravity. So the weight will act there. Then the other force acting at the pivot will be the normal reaction, pulling it outwards there. The two force balance. Right? So this is the line of action of both the weight and the normal reaction. Right? In this case, the meter rule is in equilibrium, or we say stationary, and there's no moment, as there's no perpendicular distance. Line of action of N and W pass through a point, or they coincide. Center of gravity is on the line and below the pivot. Right? Center of gravity is a pivot. Center of gravity is below the pivot. W equals to N. Now we can displace the ruler at an angle. When the ruler is rotate or displaced from the rest position, right? That forces acting the weight. This is the line of action of the weight. It's normal in equilibrium, even though N equals to W. The clockwise moment return is going to swing this way. Call it clockwise. Follow the clock. Turn this way, that way. Right? So the clockwise moment want to return the ruler to vertical position, rest position. The displaced ruler will swing and finally return to the rest position. So that is the perpendicular distance of the weight from the pivot. That's a pivot. That's the clockwise moment, W times R. Turning effect of a force. For no translation, no linear motion. What translation means no linear motion? When there is no resultant force acting on a body, the body will stay at rest, provided forces pass through a point. Right? We have illustrated that. All the forces pass through a point. All the three forces pass through a point. What happens when the forces acting on a body does not pass through a common point? The body rotates to a new equilibrium position. This turning effect affects the equilibrium of a body. Right? We will look at an example. What are we trying to show? Right? A block lying on a table is in equilibrium. Right? Wooden block is still stationary, equilibrium. N equals to W. If we apply a force there, below the center of gravity, there's your friction, opposite from friction equals to the force applied. If the force is greater than friction, then the wooden block accelerates. But the force can cause rotation or turning effect about a pivot. Right? If we apply the force further up, right, it will not accelerate anymore, right, but it will turn or rotate about that point there called the pivot, and it will it will topple over and stay in a new equilibrium position. Okay, so we define moment of a force. Right? That's how we define it to measure the magnitude. Moment about a point. Usually the point is a pivot lah. Force times perpendicular distance from the line of action of the force to the point. Right? In this case, moment of a force, we need a point, pivot P, force F, the line of action, line along which the force acts, and the perpendicular distance. 4 things. So we can look at Garfield here. Right? There's a pivot where I can turn anti-clockwise, or I can turn clockwise this way. So the weight of Garfield, the force F, perpendicular distance D, the weight from the pivot. So the moment is F times D. Right? It doesn't have to be perpendicular. It doesn't have to be acting perpendicular. The force can act at an angle. Right here, angle to the rod, direction of the rod. There's the length of the rod L. There's the pivot there, P. Right? Or we call it lever arm. So this angle is also theta, vertically opposite angle. Right? That's the line of action of this force. So there's a perpendicular distance from the pivot of the line of action of this force. L sine theta. Further away, L sine theta. Moment about P. Right? First is the force times the perpendicular distance. Right? But we can rewrite it as F sine theta times L. Right? We can take it as this L times the component of the force perpendicular to the lever arm. That's what this is saying. That's the length of the lever arm. That's the vertical component, that component of that force there in the y direction, perpendicular to the lever arm. Okay, it's just to illustrate to you how we got our L sine theta, right, for that perpendicular distance. Okay, so this one illustrate to you. Rather than make the easiest way is to find the component of force perpendicular to the lever arm. Right? That component is just pulling it only. It doesn't cause rotation or stretching only. Right? So there's a component of force perpendicular to the lever arm. Answer length of the lever arm. Right? American textbook will call this one torque lah. But A level we call it moment of force. It's called stretching only, doesn't cause any moment, doesn't cause any rotation. Right? Moment in physics have nothing to do with time. Example in moments like this. Moment of a force is the turning effect that it has. It's measured in Newton meter. Right? You cannot write Joule because it's not energy, it's a turning effect. Right? So in this case, it's force at perpendicular distance, moment about the screw. Ability of a force to make an object turn depends on two factors. Size of the force means how big is the force, how large is the force that acts at right angle to the line of action to align through the turning point of the object you wish to turn. Right? This one you want to turn the screw, that's the force. You want to know how large is this force. And that perpendicular distance, two things it depends on. So this can be small, this can be large. A small force can have the same effect as a large one if it's applied at a greater distance from the fulcrum or turning point. Right? Remember, that has a direction. That has a direction. So this moment of force is a vector. Right? It's a vector causing body to rotate clockwise or anti-clockwise. In this case, it's clockwise. Clockwise, if it's going to turn. A small force applied at a large distance to tighten a nut. So you must know what is clockwise, follow the direction of the clock. Right? Or the direction of the mini hand of a clock. That's clockwise. Anti-clockwise is opposite direction. That is anti-clockwise. In this case, it's anti-clockwise. Principle of moment. Right? This measures the size of the rotation. States that the sum of clockwise moment about any point is equal to the sum of anti-clockwise moment about the same point. Sum of clockwise moment equals the sum of anti-clockwise moment, or in short form, sum of clockwise moment, CM. ACM. Right? About any point. Right? Remember, for linear motion, the body to be stationary or move with constant velocity. Body can be stationary or move with constant velocity. Sum of outward force equals sum of downward force. The drag equals to the weight. What will happen to Garfield? In this case, he will topple over or fall downwards as he has an anti-clockwise moment about the pivot of fulcrum. How can Garfield stay horizontal? Right? Garfield has considerably more weight than Audi. Yes, Audi. That's Garfield. So for them to teeter totter, Audi has to sit a bigger distance away. Right? This has big heavier weight, lower weight. So this has to be further away, has to be shorter distance. To play the seesaw, their moments have to be equal. According to the principle of moment, their moments have to be equal. Then you can move up and down. Right? Cannot have the distance the same. the distance is the same, then it will go anti-clockwise. It will not turn at all, cannot seesaw. Right? So F1 D1 equals to F2 D2. Right? That's your F1, that's your D1, that's your F2, that's your D2. Right? When we say balance, it means it's horizontal. For a body in equilibrium, or we call it balance, sum of clockwise moment is equal to sum of anti-clockwise moment about any point. Any point. Doesn't have to be a specific point. Any point must have no rotation. Right? This condition ensure there's no rotation. Or if it rotate, it doesn't rotate faster and faster. Right? So this condition is important. Make sure it stay horizontal. Right? We can see the turning effect of forces application. Right? Pass the current, pass into electric meter, magnetic force F cause the pointer to be deflected. Okay? There's your magnetic force F, cause the pointer to rotate. Right? Here's our uses F. Can opener, tighten the nut, tighten the screw. A long spanner allow nut to be tightened with little effort. Okay? There's your force by the hand. For this one, easier. Using a handle, long handle, apply a force, cause it to rotate. Can opener, a long handle allow a small force. Right? The small force is your effort to be applied to open the can. Right? Wheel and axle. This is your axle. This is your wheel. Right? Principle of moment. We are just using the principle of moment. So if you view from the side there, that's how it is. That's the wheel. That's the axle. Radius of axle R1. Radius of wheel is R2. So we have, that's the moment. Sorry, forgotten to recharge the battery. Okay, so there's a clockwise moment. There's a clockwise moment, there's anti-clockwise moment, they must balance. So the wheel, you apply a smaller force, right, to overcome that's the weight, F1, the weight of water that you have to lift up. By making R2 large, F2 can be small. There's a small force to lift a heavy object. That can be a heavy object. Right? That's the application. Without the hammer, lifting the nail from the wooden block would be very difficult. You try to pull out the nail by itself, your fingers, you will have difficulty. But with the hammer, right, that's your distance. There's a force there. You apply a long force, greater distance away. A small force applied by you at a handle, a distance away from the nail, can be used to lift the nail from the wooden block. Right? We find another term, couple. Two equal but opposite forces whose line of action are different. Right? Two equal forces, opposite each other. Line of action is different. There's a three condition. it causes rotation. That's a P word. R, radius of the wheel, or D is the diameter of the wheel. F is the force. The two forces are equal. That's your radius of the wheel. That's the diameter of the wheel. F is the force. So we define another term, torque, or moment of couple. Torque is moment of couple. In this case, it's clockwise. Right? We will turn it clockwise. So it's F times R, F times R. So it's 2F times R, or F times D. You take one force times the perpendicular distance to find the torque. Right? So a torque causes rotation. That means you'll go faster and faster. Like acceleration in the road when it's rotating. You call it angular acceleration. Right? A force causes linear acceleration, whereas a torque causes angular acceleration or rotation. So we define the torque as force times perpendicular distance. One force times perpendicular distance of the couple. Right? In this case, it will be anti-clockwise. Okay, so that's the end of the topic. The next topic will be cover equivalent of forces, but let me just give you some question to try out. Try that one. 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 And try that one. Prepare for next video. We will answer some of this question. So try this one. Try this one. Try this one. Try this one. And that one. Okay, we'll end the video tonight. Thank you for your time.